All right, cool. I think we're set. Hello, everybody. Nice to see you. Yeah, only two problems to deal with on this week. So we can talk about some homework or anything else you got on your mind about the class. Yeah, what's on your mind? Did you solve everything?
I guess, can we look at number 1?
Number 1, yes, sure thing. This is
I
this
assume
one.
it's not too bad, but yeah, I guess I haven't gotten too far yet. Yeah, I've been trying to do it like algebraically, like
Okay.
how you, I guess, hinted in class that a lot of the proofs go. But it just gets kind of messy. Like I had some ideas for how I'm expanding it algebraically, but I can't get the inequalities that way.
Yeah, this one may be easier if you know some inequalities and definitions, which I did not tell you in class. And therefore it's like, therefore harder if you're trying to prove everything like literally from first principles, which, and I guess some sense you are. Well, let's see. Let's see. First of all, maybe we should think about it intuitively, because this sometimes is helpful.
Yeah, I was trying to think about it intuitively as well, but yeah.
So let's see. It's a little bit about this. Like you might imagine that like, okay, X and Y are discrete random variables. So they're not necessarily independent. So we see some things showing up in the problem. We have like h of x. This is like, roughly speaking, the number of bits you need to generate a draw from x. Right. On average. And similarly for h of y. And now I guess we kind of have this like kind of computer code that's sort of like, okay, to define z, so like, like do a z, kind of goes like this, like c gets like a random bit. And then if c is 1, then kind of like, let's say little z colon equals, might say draw y. I call it do a z, whatever. I'll call it draw z. Else if c is 0, we'll do z equals draw x. And then we'll like return little z. And so if we're interested in like the entropy of z, it's kind of like saying like, okay, if I run this computer code, like how many times does it call rand bit on average? Well, I guess one thing you could say is this need not be this. Okay, so this is one way to make computer code that does a draw from z. This might not be like the best way, like the most efficient way, but this is like one way to do it.
Yeah, I guess thinking about when the inequality will be tight then, or just, I thought about that as you were writing this code, like, I guess one direction might just be if they're independent, right? Because then you really do have to flip that random bit.
Yeah, that's very intuitively correct, as you say, in the sense that like imagine x and y are like independent. So like, you have this code that can draw from y, you have this code that can draw from x, and like you might imagine that like in principle there could be like some code that like it's like called draw x and y, and like it returns a pair, and like potentially if x and y are not independent, there might be like some most efficient code for this that like, I don't know, does something smart. But the idea is that if x and y are independent, then like, well, this thing may as well just be like one call to draw y and one call to draw x, and it just returns both of them intuitively. And then you get the feeling in that case, like, okay, if that were the situation, like if you had to make code for like draw z, you kind of say to yourself, well, what am I going to do other than this like code? Like it seems like it should be the best. because there's no way like you can get, I don't know, any savings. This is the idea when X and Y are independent. Now, like, I guess like normally, or I guess, you know, one thing to think about is like the way you can prove an upper bound on entropy, like if you have some random variable Z and you want to show that H of Z is like at most something, you could do this by like, you know, in some sense, like giving some code for drawing like Z and showing, you know, it uses at most, you know, T bits, you know, or T calls to rand bit on average. And then that would kind of imply that the entropy is at most T. Of course, you got to be a little bit careful about this because, like, you know, in some sense, the entropy is not literally the number of average number of, I mean, this will prove it, but like, it's not literally the number of bits used on average. Like maybe this is only exactly right when the probabilities all have denominators that are like powers of 2. But I guess this is at least one intuition. And I think this code kind of matches up, syncs up with like this intuition in the sense that this code's like always using like 1 bit for C. And then again, intuitively, like half the time it's using however many bits you need to do X, which is this, and half the time it's however many bits you need to do Y, which is this. So this is like one of those things that like comes up a lot in like, you know, information theory where like there's a very strong intuition behind some, you know, expressions or inequalities. Then you have to take a little bit of care to actually prove it.
I guess for the intuition of the other side of the inequality, like this might be kind of obvious, but I guess I can just say it that if they're the same random variable, I guess, then you don't have to flip, right? And so
yeah, for example, indeed, like in a specific case, just as you say, like if X and Y happen to have the property that like, you know, X is literally Y always. So, you know, draw X and Y would just be like, you know, you could say, you know, X equals, you know, draw from X, and then like Y equals X, and then return X, Y. Then indeed, as you say, like you don't have to flip the coin. Like you can just return one of them. Like you can just, you know, call draw X basically, and this will have the right distribution. So that's in particular, like in this very special case, like, you know, H of X will equal H of Y, and so this will just be H of X. Yeah, so those are some intuitions for when this will be tight. Now, can you also think of an intuition for why this lower bound is always true? We saw like, we were just talking about intuition for like, what's a case when it will be tight, but like, what's an intuition for why this lower bound will always be true?
I mean, I guess just Z depends on X and Y, right? Which depend on this C, which gets flipped with 1/2 each in each case, or probably 1/2 in each case, and then so I don't know. That's like the intuition for why it's the average of the entropies, I guess. I don't know.
Yeah. You know, I guess like an intuition for like entropy lower bounds, you know, like H of Z is at least U, kind of like saying like, you know, again, like always like on average, you know, to communicate or store or draw, store a draw from, or, you know, create a draw from Z, you like any algorithm or any method like needs at least U bits, random bits. And I don't know, I guess in some sense, like, it is true that like half the time, like you're going to have to be like communicating or drawing or storing X, and like half the time you're going to be doing Y. And there could be some savings if you were required to draw like X and Y. If you could generate X and Y together, if they're not independent. But I guess there's some intuition that like, well, be that as it may, like half the time you have to at least generate X, and like half the time you have to at least generate Y. So there's some kind of lower bound. So I mean, I guess, okay. I mean, this is a little bit evading the final details of like, okay, how do you actually prove these things? But I guess it's a good start to have some intuition. Now, in terms of how to prove it, maybe that's another matter. I don't know, does anybody have any suggestion?
We tried to use a probability technique, but we found that was a little bit complicated. So we decided that it was easier to just stay with the entropy kind of the forms of the entropy and like conditional entropy kind of stuff that was in lecture.
Yeah, you can try to, I think, attack this using like these objects we talked about, like conditional entropy and like mutual information and things like this.
Yeah.
Yeah, I don't know. I mean, maybe we should try to prove one of these inequalities. Let's see, which one is more enjoyable to look at?
Maybe the right one, maybe.
The right one, okay. Yeah. Well, I guess for the right one, we had this intuition, right?
Yeah.
So yeah. You can try to go ahead.
We were maybe thinking you could use the forget what if this is the chain rule, but like h of z is equal to h of z given c plus the mutual entropy of z and c.
Yeah, I was thinking like, did we do that in class? I guess we did. You're saying like h of z is what now?
H of z given c. Plus mutual information of z and c.
Yeah, let's see if we agree that this makes sense. Yeah, I mean, I guess this is how it's defined. I mean, this is the amount of like savings you can get when generating z and c together. And this is how much it costs you to generate c. This is like how much it costs you to generate z, like if you sort of already generated c on average. So okay, again, these are like maybe intuitive quantities, but okay, we also have these as definitions basically.
Right.
Let's see.
And
so we may want to like match this up.
Yeah.
I suppose we should remember like, what is this quantity? H of z given c.
Expectation.
Yeah, this is really an expectation over like sort of
c.
Little c drawn from capital C of kind of the entropy of the random variable like z conditioned on c being little c. It's kind of funny notation, but so I mean, since c is a coin flip, it's really, I guess, just half entropy of like, okay, well, writing it slowly, z conditioned on c being 1 plus a half entropy of z conditioned on c being 0. Okay, but this is, I guess, x and this is y.
Right.
I guess that's good. And then I suppose that's getting us part of the way there. Then we just have to ideally show that this is at most 1.
Right.
This should be doable though, right? I mean, if you remember, well, a couple of things, but for example, as we talked about in class, this is like the savings you can achieve when generating Z and C together as opposed to separately. But, the most you can ever save is everything.
Yeah.
And, the everything for generating C is 1 bit.
1.
Yeah.
And we know that mutual information is positive from Jensen's inequality as well. Right?
Yeah, or I suppose I stated this as
Yeah.
well. So yeah, I guess one can put these things together from things that I stated in class, most of which I didn't prove, but well, if you want, you can like write down proofs of them yourself, but you can, I suppose, take it also for granted, the things that I stated.
Right. So we
Oh,
found
actually, wait a minute. We're in
what?
like good shape though, because then we're pretty much done, right? This also helps
Yeah.
the left-hand side.
Yeah, exactly. But
Okay,
basically,
so
that
maybe,
like +1 term is mutual information.
yeah. So maybe one can, well, if you're feeling noble, like also write some, I guess not, I was gonna say like write some proofs of like things like this, but you might want to do it for fun just to like see what's going on, but I guess this more or less does it.
Yeah. So we tried to do this using probability statements, but it was really tough actually to
It's
get
really
it to
bad.
work. Right. Yeah. I mean, not bad. It was just like hard because like we don't know what the domains are of probability. Like the ranges that the X can take and the Y can take are not necessarily related. Like if X was like A, B, C, D, and Y was like 1, 2, 3, like it wasn't clear how you could like do it. Like if you do it this way, then everything just like works out. But if you take the other one, it's hard to like figure out like the intersection of the ranges of the values in some sense.
Yeah, I see what you're saying. Like it's a little bit of a mess. Well, maybe let's just try it and see like how it goes and goes wrong. Or like, okay, so X has some range, maybe R sub X, and Y has some range, R sub Y. So I guess like the range of Z is the union of these things.
Yeah.
It's a bit funny though, like if these are just like abstract sets, it does seem like a little bit weird because like they could have some intersection or
Exactly. Yeah.
although it shouldn't somehow really matter. Like you should sort of be able to pretend that they're disjoint, but like I guess it's not immediately clear from the definitions. Maybe not even. Okay. Yeah, probably not. Okay, so, but you could just be like, okay, I'm gonna try to do this like really blindly. So Z has this range, so like the entropy of Z is like the sum over all little z and like the range for Z, which is this thing.
Right. Right.
Of like probability that Z equals Z times log of 1 over this probability. I do see it's like starts to be a bit of a mess though, because okay, what is the probability that Z equals a particular Z? Yeah, it's sort of annoying. Well, I guess it's half the probability that like X equals, that's not a probability. Probability that X equals little z plus a half probability that Y equals Z. It's a bit funny though, because you're like, oh, if little z is like not in the range of X, I guess we're relying on the fact that this is 0 if little z is not in the range of X.
Right. So you have to
But you're starting to
redefine
maybe
it
a
in
little
some
bit like
sense.
worry about type checking.
Yeah. Yeah.
But maybe it's okay. I mean, okay, we could then like plug this in and be like, all right, that's sum over little z of half probability that X equals Z plus probability that Y equals Z. Then it doesn't look too great because we have like this.
Yeah, exactly.
This sum, but well, one can persist. See what happens. Because because, okay, like there's no move to try here other than like breaking this into two sums. So, all right, we have like half sum over z, probability that x equals at, little z times the log of this kind of annoying expression.
Right. It's not very clear how to split that though, because like logs are nice in when you have multiplication, not so nice when you have addition.
Yeah, that's true. So I guess the game here is going to be like, you can artificially think of like x as taking values. You can like think of x as taking values. I can't write today. Taking values in like the range of z. Like it's just like, okay, they might have like a bunch of values, probabilities that are 0 if it's like some element in the range of z that x doesn't take on, but you could say that's okay. And then, okay, then this expression, I mean, whenever I like see something that looks like this, I get the temptation to write it as an expectation. Expectation over z drawn from x. I mean, if you just formally convert this to like some probabilities, it'll look like this. So expectation of z drawn from x of this expression log base 2 of this kind of gross thing.
And then I guess like here the probabilities are gonna be, yeah, this is where it was like tough because we didn't know like what the probabilities of y were here, because it depends on the range, right?
Yeah, I guess this is although this is also the point where like you can take the hint that like in information theory, like there's only so many tricks, and like the only trick that we haven't yet used is basically Jensen's inequality, or the fact that log is like a concave function. So
right.
I always just remember like this. Okay, log somehow looks like this is like the plot of log. So like if you take the average of its values at like 2 points here and here, the average of the value is, it's a terrible drawing. The average value is like maybe this green point, but like that's below this orange point. So okay, so it's concave, so that means like the average of some values is smaller than the function applied to the average. So this will be at most log base 2 expectation z drawn from x of 1 over, oh yeah, this is not going to look so great, but we'll see. We'll keep going, I guess. I wonder if, okay, yeah, we'll keep going, but like, yeah, like probability that x of little z plus probability under y of little z over 2. That doesn't really look like a dream quantity though, because this 2 pops up here.
I think there's a half constant in front of everything, right?
Yeah. There's a half out here. Yeah. I mean, maybe it's okay. You could say that, okay, this is, let's just keep going like on autopilot until we get stuck, like log base 2. We're going to turn this back into a sum over z, probability that x equals z. It's 2 over, doesn't look so great. X equals z.
Yep.
Plus probability that y equals z. Your dream here is that like somehow this would like nicely, some nice algebra would happen.
Right.
It doesn't look super promising. We have some expression that looks like 2a over a plus b. This is a and this is b. One could also see what are we trying to do here? I guess we're trying to show that this is at most the average entropy is +1. At least so far, since the move that we made was this.
Yeah. I would like drawing inspiration from the like maybe what we were guessing, like you would have to introduce some form of mutual entropy here, sorry, mutual information here. But it's not like from the completely abstract way of like looking at it through conditional entropies, there would have to be some like introduction of like and mutual information, but it wasn't clear how we would introduce that in some sense.
Yeah, I mean, I guess that's a good point in the sense that, like, okay, if you look at like this proof sketch that we looked at, this
Yeah,
was like an equality, so nothing had happened,
right.
and then we had this inequality here, but this was at most
Mhm.
1. And really, I guess as you're saying, like the mutual information, we kind of use that the mutual information between A and B is at most the entropy of B.
Right.
And one way to know that is to recognize that this is the entropy of B minus the entropy of either B given A or A given B.
Right.
I suppose it should be.
It's A given B.
Let's
Sorry.
see.
I think it's B given A.
Yeah, I guess.
Yeah.
Yeah. Well, in either case, and then you can recognize like, oh, but entropy is non-negative.
Right.
And that's
Right,
how you
right.
can get this is almost this. So like in the
Right.
end, like the arithmetic will come down to, or like the inequality will be because the entropy of some expression, you'll get like maybe the entropy of some expression somewhere and be like, oh, this is non-negative, which is, I suppose this is just because, why is entropy non-negative? Entropy of like A is like sum over A, probability that A equals A. I mean, it's times the log of 1 over this probability.
And this
And this is
also
like an
tangent.
average. So like it's the average of some
Right.
non-negative number. So it has to be non-negative. So actually that means that like, actually, you know, this is kind of like retconning the whole proof, but like, it kind of means that like to prove this upper bound, we didn't use like anything that involved like Jensen's inequality or convexity. We only use the entropy as like non-negative.
Right.
So actually it kind of tells you that like, this is not the right move because,
Yeah.
and I think I even kind of see that now, like,
Yeah.
because this looks kind of bad, maybe you wanted to actually use, yeah. But anyway,
Yeah.
so it must be that instead, like you somehow, you should be able to just like manipulate this until you get, like a half the entropy of X plus a half the entropy of Y plus 1 minus something that's like manifestly non-negative.
Yeah, exactly. So some like if we rewrote like the conditional entropy kind of equation in terms of probabilities, I think it would work out. But it wasn't like obvious to do that when you start off, because if you just use the probability stuff, I feel like you get stuck somewhere here.
Yeah, I mean, you have to be a lot smarter. I guess it goes to show that like it's like a nice feature of like information theory that like, if you had to prove it by like manipulating these formulas, like it would seem to require like a lot of smarts and insight or like good guessing or something. But like somehow, if you've like named all of these quantities and have like natural intuitive meanings for all of them, like it really guides you on like how to do the manipulation.
Yeah, exactly. Yeah,
I mean,
precisely.
Yeah. I mean, I suppose like the thing to do actually, like when we got to this point is, I mean, we kind of know in the back of our heads, we need like entropy of X to show up. And like here we have something, half the entropy of X actually. We have something that's like moderately close to being entropy of X.
Right.
You can probably just like, you know, forcibly get entropy of X in here. So like here we have like sum over X probability, oh, actually it's Z, but sum over Z probability under X of Z times like log of something, some weird thing involving stuff involving Z. And whoa, Sorry, I lost my screen here. 1 second. Okay. And you can be like, well, I really want to have entropy here, so I'll just like add and subtract something in order to put it there. So you can like add the entropy of X and subtract the entropy of X. And I guess when you so that's doing nothing, but like when you subtract the entropy of X, you'll get minus sum over Z probability X Z log 1 over probability of X Z.
Right.
And then you're like, oh, okay, this is looking not so bad because logs have these properties that like you add 2 logs and it like multiplies. So like you'll get sum over Z, probability X of Z, and then maybe something that's like not terrible, like you'll get log of, well, probability X Z times whatever this stuff involving Z was.
Right.
And I guess it was this. If you multiply it by this, well, it's still not looking that great, actually. But
I think it gets closer to what the mutual information kind of thing is, because but like I think you have to use this with the probability of Y thing and put them all together, and then you'll like have an aha moment and figure out that this is actually the same as the mutual entropy or something like that.
Yeah, in fact, like I think probably you'll like, oh, this like you have this like 2 in the numerator here, and you'll probably be like, oh, this is actually 1 over a half. And so like I kind of see that like the entropy of like a probability distribution that's like a half is coming in.
Right.
But I mean, I guess like once you finally do all this, what it'll eventually amount to will exactly be like just writing down all the proofs of this like simultaneously and like.
Yeah, exactly.
Yeah.
It was just an interesting kind of thing to like realize that like because my intuition would be to go to probabilities first, but here probabilities actually lead you down like a very tricky path.
Yeah, exactly. That's very true. Yeah. So it's really nice to have this operational meaning of these quantities to get the right reasoning.
It's funny, like looking at this, you might come to understand how someone could even come up with the definitions of like mutual information and conditional entropy in the first place.
Yeah, that's a very good point. Like, if whatever reason, like you only knew the definition of entropy and you like wanted to prove this, you almost like are kind of forced, not forced, but you were like, you could see how you would invent like, mutual information and conditional entropy and things. Yeah, that's a good observation. Well, should we talk about the other one? Did you solve the other one?
Sure. Yeah, this is a little trickier, I think, but yeah. Maybe someone who's like
Somebody else have some
got
thoughts
it.
on it?
Yeah.
Yeah, I think you can like show that one individual bit, the probability of it being, I forgot the word for it, but like the probability of A times like one individual bit from the output generator is negligible and n close to the uniform distribution. And then you could use that to like inductively build out that the final output is negligible and n close to the uniform distribution.
Yeah, what's the story here? I like to draw this picture. This one's like output. Yeah, I forget what I called this length. I guess it's like oh, I called it n to the 10. Okay, well, yeah, so this whole thing is like G prime. And maybe there's like n to the 10 output bits here. Yeah, so I mean, I guess the way one tries to break that, I mean, okay, what do you have to prove? You want to show that G prime, G is like a good PRG. Implies G prime is a good PRG. I guess you'll always prove this by proving the contrapositive. So like if G prime is a bad PRG, implies that G is a bad PRG. I guess you'll do this, right? Because these are really like for all statements. Like to say that G is a good PRG is just like say for all adversaries, this adversary fails. And once you do the contrapositive, like this will be like an there exists statement, like there exists like an adversary that can like break your PRG. And there's like an adversary breaking G prime. And now we have to deduce that there's like an adversary breaking G. So, this is more in the spirit of like designing algorithms. We have some algorithm that beats G prime. Now we have to use it, some kind of subroutine or something for an algorithm breaking G. So, it's much easier for us to like prove existence of things than to show for all type statements. So yeah, you might imagine like, yeah, I wonder if we can imagine. I'm just wondering if you can imagine like sort of a specific case here, like, I don't know. So what does it mean that like, we have some adversary breaking G prime? Well, let's call this adversary A. Maybe we should call it A prime, but anyway, A. So it can like basically what's the deal? A can like look at the output of a draw from G prime and like notice that it's not the uniform distribution. So it can like look at all these bits and say like, oh, that's not the uniform distribution. Now the trouble is like, there's many ways that can happen. And like, what do we have to deduce? There's like some other algorithm that can like notice that G is like a bad POG that can look at all these bits and be able to notice that like they're not uniform. So for example, maybe we could like do like a special case. Maybe the adversary A has the property. Well, maybe like this first bit is always equal to the last bit. That would be like a way in which G prime would be like broken. I mean, if like the first bit of these end of the 10 bits was always equal to the last bit, you'd be like, this is not uniform distribution. Like that's only supposed to happen 50% of the time, and it's happening 100% of the time. So what could one do? Like imagine, it's like some crypto challenge out there, and somebody will give you like a big prize if you can find some adversary that breaks G. And you kind of notice that like, oh, if you do this construction, if you take like n bits, you plug them through G, plug the the first this through G, and then plug this through G, and you collect all these bits, then like this bit is always equal to this bit. How would you build an algorithm that like directly broke G? I guess this is an example of like one thing we need to do. Like eventually we have to take like any method of breaking G prime and turn it into a method for breaking G. But let's just assume A is like a simple method. Happens to work. How to do it?
The algorithm could just output the value in the last bit, like ignore all the other bits.
Interesting. Let's see. So let's say, okay, so this is your algorithm. So like, let's say n is 50, maybe 20, 10. I just want to like write something on the screen here. Let's say, okay, let's say n is 10. I don't know if this is going to be a good idea. So then, you get a draw, like you get like a draw of 11 bits, and they look like 1 1 1 0 0 1 0 1 1 0 0 1. How many is this? 1 2 3 4 5 6 7 8 9 10 11. Okay, it looks like this. You have to guess like, hey, is this just like 11 random bits, or did somebody get this by like plugging 10 random bits into like G, 10 uniformly random bits into G, and it spat out this. And kind of the only thing we know is that like if you do this whole construction, like this bit will always equal this bit. So what was your suggestion?
The adversary could output the bit, which always equals that last bit.
So wait, oh, let's say the code breaker or the PRG breaker is you, the person trying to win that prize. Just output this, you're saying.
Yeah.
So I guess in order for you to win the prize, like it must be the case that this bit is not 50-50 balanced, because like if this were truly random 11 bits, then this would just be like, 50-50 coin flip. But you're kind of postulating that it has to not be a 50-50 coin flip.
Right.
Not so sure.
Wait, so is this set up that the very last generator's output bit is always the same?
No, like maybe we should even imagine, okay, maybe to make things, hopefully this will make things simpler. Let's imagine that this is not n to the 10, but it's 2. So let me try to draw this picture again then. So imagine there's like some, NIST puts out this like, standard like generator G that like stretches 10 bits to 11 bits. Okay, these numbers are obviously too small, but like somehow like nobody should be able to like, if you plug 10 random bits into G and like look at the 11 bits that come out, it should be like hard. It doesn't really make sense if they're like 10 and 11, but like it should be hard to notice that these 11 bits are not uniformly random. But now, like, let's suppose you're like really enterprising and you notice the following bizarre feature that like, if you take this G and you put in, any bits here, like x1 through xn, okay, what comes out? What comes out is like y1, y2, ... y10, oops, I should say 10, and then y11 comes out. And you notice that like, okay, if you do this and then you feed this back into G, what comes out like z1, z2, like z10, z11, you notice that like, weirdly, like y11 always equals z11. Maybe we should like, maybe this should always be like 10,000. This should be like 10,001. This is a little bit more. Should also use like large numbers that don't themselves involve zeros and ones, because then it's like, it's confusing. Like maybe this should be like stretches 7,000. Okay, never mind. I'll go back to 10 and 11. Okay, so yeah. So, you want to like, get some like, G breaking prize, but you didn't quite break G. Like you don't obviously have an algorithm that looks at 11 bits and says like, aha, I can tell this is the output of G and not just like 11 random bits. You have this like weirder thing where like you happen to notice this like fatal flaw, potentially fatal flaw in like G's system, in the sense that if you like kind of do this weird thing with G, like y11 always equals z11. So yeah, now what? This is like, this is somehow a security flaw in like G, but like how do we exploit this security flaw?
I guess maybe something like you feed y1 through y10 into G as part of the adversary. And then if y11 equals z11, you output 1. Or
well, what is like y1 through y10? So you have to actually, I mean, to really break it, like, how do you, oh, maybe I understand what you're saying. So to break it, you have to write an algorithm like mycrack, where like I'm trying to crack this G. It's going to get, maybe yeah, as you might want to call it like y1 through y11. And like you're trying to figure out like, is this, 11 random bits? Or is it like G applied to like 10 random bits? And we got to kind of guess. So what is this code going to be?
Oh, okay. So you take y1 through y10 as a seed, like the adversary takes y1 through y10 as a seed to G,
Mhm.
and then if the output of that that generator is like z1 through z11, and
Yeah,
z11 equals y11, you output 1.
yeah, very good.
Yeah.
So you're saying, I mean, I think this is going to work. So you're saying let z1 through z11 be the result of applying G to y1 through y10. And then you're saying like if, z11 equals y11, then you'll like return, 1. That like means like, I think this is, pseudorandom, like it was this case. Else maybe you'll return 0, meaning like, basically you're like, I don't know, could be a fluke or like, fine, maybe you think it's like random, but
Right.
good. So let's see. There are two things to think about. So what you actually need to prove is that like need to show that like probability that like my cracking algorithm, when given 11 uniform bits, outputs 1, is quite different from like it's not approximately equal to the probability that like my cracking algorithm will return 1 when it's given like G of 10 like random bits. So one of the things that you think about, I mean, first thing to think about is like, what is this value?
It's going to be half,
Yeah, why?
because there's 1/2 probability that you get a 1 or a 0 at z11. Or it's half plus minus negligible n. Or wait,
Yeah, what is it? What is it exactly? Maybe somebody else. Well, you can also pipe up, but like, I hope everybody is thinking about this question. I think it's exactly a half. But why do I think that?
well, the probability of the first bit being a 1 or 0 is a half.
Which first
or I guess
bit?
like sorry, like the y11 equivalent.
Yeah.
But then you feed y1 through y10 into the generator to get z11.
Yeah.
And y1 through y10 is going to be this uniformly at random.
True.
So then z11. Well, are we assuming the generator is a PRNG here, or like a cryptographic?
No. I guess, I mean, we kind of don't know whether it is or not. I mean, the whole goal of this proof is actually to show that it isn't a good PRG. But
right.
I mean, I claim
Oh,
that
maybe
we can prove this about this no matter what.
Maybe like what z11 is, like z11's like probably 1. Like the probability that z11 is 1 is going to be like p. And probably at 0 it's gonna be like 1 minus p.
Mhm.
Maybe the condition based off of whether something like that, where if it's so then if the first bit is 1, then you have a probability p of the matching up, and that happens with probability 1/2, so 1/2 p. And then if the first bit is 0, you have a probability 1 minus p of the other bit being 1 minus p. That happens with probability 1/2. So then the p's cancel and you just get probability 1/2.
Yeah, I think I know what you just said. So like, I think you said the following. We don't know too much about G, but you're saying, let's just focus on like, what's the chance that Z11 will be 1 when we plug in these 10 random bits? So like, and you said let P be like the probability that like Z11 equals 1, you know, when Y1 through Y10 are uniformly random, which they are in this like story we're thinking about. And then you were like, okay, so we return 1 if Z11 equals Y11. So you might say like, what is the probability that Z11 equals Y11? Well, first thing you need to ask is like, are Z11 and Y11 dependent or independent?
I guess they're independent, right?
Yeah,
Because
they're independent because like Z11 was part of this Z, but like that came from just plugging G into like Y1 through Y10. But you know, we're hypothesizing here that Y1 through Y11 are like 11 independent random bits. And so Y11 is independent of Z11. So then you're right, like the probability they're equal is, well, there's like a P chance that Z11 is 1 and like a half chance Y11 is 1. There's like a 1 minus P chance that Z11 is 0 and like a half chance that Y11 is 0. And this adds up to a half. I might also
Right.
just say like a little bit more casually, like, you know, Z11 is something. It's either 0 or 1. We don't really know a lot about it because we're not assuming too much about G. But anyway, whatever Z11 is, like Y11 is independent of it. So like the probability that a random coin flip equals like some fixed thing is 50-50. So okay, so good. So we believe that this quantity is a half. So now we have to hope that like this quantity, which is, I don't know, like I need a better color here. This purple quantity is like not around a half, or at least is like non-negligibly different from a half. So, okay, what is the probability of this? Or yeah, what is this
1?
quantity? 1, let's see. Yeah. I mean, that was like our whole assumption, our whole game that like, indeed, like whenever you plug, well, wait a minute, is that so?
Isn't it like,
Yeah, I guess so. Like if we call these X, these 10 random bits, we were kind of our, you know, the security flaw that we notice, if you take like any 10 bits X and you plug them into G, that's what's happening here. You plug them into G and you get Y1 through Y11. That kind of goes up here. And then you like save Y11 and you plug Y1 through Y10 into G again, which is what's happening here. And you get Z1 through Z11. Then yeah, like the security flaw that we're hypothesizing is Z11 is always equal to Y11. And so you're right, this is exactly 1. And then we're like, hey, we broke it. Like we have this my cracking algorithm has a property that, you know, if you give it truly 11 random bits, there's a 50% chance it outputs 1. But if you give it like the output of the pseudorandom generator, there's a 100% chance it outputs 1. So it's really great at noticing the difference.
yeah, this is way simpler than I was trying to prove it directly, and basically using like proving that every single bit that's outputted is an adversary can't see if it's like more than negligibly different than the uniform distribution. And then the concatenation of all of those bits is negligibly close to the uniform distribution. That's definitely more
Yeah. Well, I mean, I think it may be. Yeah.
it wasn't too it's not I don't think it's too bad though, because you can have a pretty short argument for like every 1 bit being close to the uniform distribution, and then the concatenation can then be induction, where you're only adding on like a constant times negligible and n, like distance from the uniform distribution with every single concatenation.
Yeah, you have to be a little bit careful though, because it's not like a very traditional notion of distance. Like where this, computational indistinguishability is referring to like a notion of distance that's like a little bit non-traditional. Distance that's non-traditional from a statistics point of view, in the sense that like it's about the ability of polynomial time algorithms to distinguish the two strings.
Right. So yeah, using the definition.
Yeah.
Like the proof would use a definition. Of non-distinguishability, but
Yeah. So for example, let's see. Yeah. So for example, maybe we'll do like one more test.
Sorry,
Like, okay, maybe this.
Can I ask
Yeah.
Can I ask like a high level kind of thing?
Yeah, go for it.
How would we so what we're trying to show is that this output of G prime is good in some sense, right? Like it's like close to it's like indistinguishable by a poly time algorithm to be able to distinguish it from some uniform. How does what was the sketch of like what we were doing? Like how does like being able to break G relate to like the final thing? Like what was the sequence of steps in the proof that we were trying to show again?
Yeah, it's kind of like, okay, maybe I don't know if this will help, but it's kind of like over here. So this is what we're like asked to show originally. If G is a good pseudorandom generator, being vague here, but then G prime is a good pseudorandom generator.
Okay.
And the contrapositive of that is that if like G prime is a bad pseudorandom generator, then G is a bad pseudorandom generator.
I see. Okay, cool.
And what is the definition of G prime is like a bad pseudorandom generator? It means there exists some adversary that can break G prime.
Right.
Yeah, we have to conclude that there's like some adversary breaking G.
I see. And we're saying that like if G prime is a bad pseudorandom generator, like we gave an example for that being a bad pseudorandom generator, but in general, like all we need to do is assume that there exists some breaking G prime, some adversary that can break G prime, right? Like the thing that we just did, that was showing that you could come up with something like that potentially if you have a bad pseudorandom generator. Is that correct?
Yeah, so I mean, what is the definition of being a good pseudorandom generator? It's like saying, G prime is good, implies, well, it's by definition, like for all, adversaries A, A fails to tell the difference between, truly random bits and, output of G. So therefore, if you just negate this, G prime is like bad, is like there exists some like adversary A such that A like can like sort of tell the difference between like the random and output of G prime.
Right.
So like when we're showing, G prime is bad implies G is bad. G prime being bad is like, oh, there exists some adversary that does some stuff. And we need to show that G is bad. So we need to show there exists some other adversary that does something involving G.
I see. So basically we're saying that there exists some adversary. So we're taking as a postulate, there exists some adversary that can break G, right?
Prime.
Oh, that can break. Oh, I see. Sorry. I think I got it wrong. Okay. Yeah, that makes sense. So we're saying that there's some adversary that can break G prime, and now we want to see how we can use that to break G. Okay, that makes sense.
Yeah.
All right. Sorry, I think I was just a little confused.
Yeah, no worries.
Thanks.
So actually, just there's one like more way to think about it. Let me just like set up and think about for one moment, like one more example. So suppose like say, you were the person like playing around with G prime, and say you noticed the following about G prime.
Oh, sorry, I have to get going, but
yeah, no worries. Yeah, sure, no problem. I'll just like take 2 more minutes here. So you notice the following thing about G prime, like you notice that like, okay, if you put in like random bits here, like you outputted this and call this A, And then you fed these things back into G. And you call this B. And you fed this back into, oops, my drawing's getting sloppier and sloppier, like C. And you fed this into G again. And you called this like D. Like maybe you noticed, like weirdly, like 95% of the time, and that's 95% of the time is respect to these random bits, like, I don't know, A equals like the AND of C and D. And you're like, that's weird. Like if I were, you know, if these bits were truly random, then like this would happen like 50% of the time. But like if I do this bizarre construction like G prime, like it's actually happening 95% of the time. Well, you would say to yourself, man, this is like gotta be like some sort of weird security flaw in G. Like G, if G was like, you know, a totally random function like it's supposed to be, like this equation would be happening like 50% of the time, but it's happening 95% of the time. So it is like some kind of security flaw in G. But now like you need to like, how would you like explicitly demonstrate like a direct security flaw in G? Like not to say like, oh, if you know somebody gave you again, like imagine G maps like 10 bits, just for clarity, to 11 bits. You had some like, you know, you want to like get your like my breaking algorithm that like gets in 11 bits, y1 through y11, and it's supposed to guess like, hey, are these just like 11 random bits, or are they actually the output of G on 10 random bits? Like what code could you write here, like exploiting this security, well, exploiting this like weird security flaw, if you will, that would just like directly guess whether these were like 11 random bits or they were the output of G.
Wouldn't this just be like kind of the same code as what was
Pretty
what we did
much,
before?
right? Yeah.
Just except with like the equals to, with this like AND thing, you just run the y1 through y11 maybe like 4 times through G, and then you check to see if like, or not 3 times, and then you check like if a y11 is equal to like C and D or something like that.
Yes, but now we might see if it's like a little bit trickier. Well, you're saying like what you're gonna do is you're gonna say like, oh, I'm gonna do, like I'll save y11. This is what I'm guessing you said. I'll save y11.
Yeah.
And then,
Yeah.
I mean, I'll basically do this, right? Like I'll let, you know, I'll do G of like y1 through like y10, call the last bit B and the
B.
rest Z. And then I'll do like G of Z and call the last bit, you know, C and the rest W. And then I'll do like G of W and call the last bit D. And then like, you know, I'll like return, you know, whether or not like A equals like C and D or something.
Right, exactly.
So here's where it gets difficult, I guess. We would want to do the same thing here. We would want to show that this probability is quite different from this probability. And I guess we know this thing.
Right.
This is like not the 95% I was talking about.
That's right.
What about this thing? This is like the probability if I, what if I take this code and I just give you 11 truly random bits here? Then you're like, okay, this will be a random bit. Actually, I guess this is going to work. So maybe let me change this like crack to B equals C and D. I think that will make it potentially a little bit more interesting. So you're like, okay, this will be a truly random bit, but I guess anyway, we're not using it. Then we call G on y1 through y10, and we get back B. Now these were truly random, but now B actually, it's not necessarily random. I mean, G is like B is like the last bit of this pseudorandom generator applied to 10 random bits. So if B were truly random, then you'd be maybe in good shape because you'd be like, oh, this is like a 50-50 bit. So maybe this is like 50-50, but it's actually a bit more subtle because you you don't know if this is
Seems
like
like-
50-50 or not.
Yeah, it seems like you've shifted the whole thing a little bit, right? Like if you're taking the output of if you're given in y1 through y11, that's essentially given one round of G. But
Mhm.
if you were given like if you have a truly uniform thing, then it's basically giving X in some sense. So basically the outputs you get here are like A, B, C, D, but like the output you'd be given like if it was truly uniform would be like something like that's like X11 and then A, B, and C instead in some sense. So you're comparing like B is equal to C and D to something where it's like X11. I
Mhm.
mean, there's no X11, but theoretically an X11 is equal to like B and C in some sense, right? Is that correct?
Yeah, I didn't fully get what you're saying, but I think so. Actually, to make it like even simpler, like let's even, I keep changing this security flaw. Let me just say let's change it to like B equals C. Let's say this
Okay.
part is not even happening. Um,
Right.
Then we don't really need this. And we don't really need this.
Yeah.
So I guess the point is like, it's no longer obvious that like, I mean, before we were like relying on like, okay, if y1 through y11 is truly random, like the probability this, my break returns 1 was a half. But that's no longer so obvious. Like, it's now kind of unreadable, I guess. Because we don't really know. I mean, let me just rewrite it. Like what we're doing is, my break on like y1 through y11, just to be a bit more clear, we're saying like kind of z comma a is g of y1 through y10, and then oh wait, maybe we're calling this B. And then, W comma C is like G of Z. And then we're returning whether or not B equals C.
Right.
But if these are uniformly random, then definitely these are uniformly random. But now, if you ask like what's the probability that B is 1 or 0, well, we called it, before Lev called it like P for like the probability B,
Yeah.
1. But then luckily we're kind of comparing it against a uniformly random bit, but now we're not. We're comparing against like an even more kind of convoluted bit, like the C that we get out of doing this. So you might say like,
Right.
who's to say that like, why should this be a half? Like maybe by some like weird miracle, it's like also 95%.
That's true.
So I guess like, I better wrap it up, but I guess the point is that like this, I mean, the final conclusion is actually this breaking algorithm might not do the job. It might not be the thing that works, but you'll be able to like develop like maybe 1 or 2 or 3 different like breaking algorithms, like my break 1, my break 2, my break 3, and you'll be able to argue that like one of them has to work.
I see.
And maybe a little hint for this is like you might be like sad if like B is, you might be sad if like B is not like a 50-50 bit, because I don't know, that's going to like make it difficult to analyze this. But suppose B isn't a 50-50 bit. Well, then you've kind of discovered a different security flaw
Right.
in G. Like apparently if you take 11 random bits, throw away the last one, plug them into G, the last bit is not 50-50. Well, that would be like a different security break or security flaw in G, and be like a different method of showing that G is broken.
Cool.
So like either you could directly exploit that one, or if that one worked, doesn't break G, then you've kind of gained some new information that this last bit is 50-50, and then, well, you have to start doing some more reasoning, but at least these are some of the ideas that you'll need.
Cool. Yeah, that's interesting. So it seems like you have to like create like this like sequence of things. Like if one is not sufficient to like prove something, then you know that that G is like broken in some way. If G is broken in some way, you have to kind of like narrow down which way it's broken in some sense.
Yeah, it's a little subtle. I mean, I think
Mhm.
if you like run through like this exact example, you'll probably get the general idea. I mean, it's kind of a way to solve it, like, maybe solve this exact example, and then if you still don't get it, like maybe make up a slightly more complicated example and try to solve it. But I
Cool.
think like one general phenomenon as well is that, if there's like 5 bits down here, if your weird method of breaking G prime involves like 5 output bits down here, then there'll be like maybe like
Mhm.
5 different potential breaking algorithms, and like at least one of them will have to be breaking G.
I see. So it's like if there's like some way that incorporates like how many ever possible like outputs you have, then you have to you can basically break it down into all of the possible ways that it could fail with all of them. So it's like if you have n to the 10 like possible outputs,
Yeah.
then potentially there might be like if it's like excessively complex, which means that you have to like figure out some combination of all n to the 10 of them. And you can break it down into smaller and smaller breaking algorithms potentially.
Yeah. But like another
Cool.
feature to remember is like, oh, you can kind of see like this picture is somehow irrelevant. One thing that's like working on your side is like, in order to count as like a break, you just have to make an algorithm that like slightly non-negligibly can tell the difference between uniformly random and like the output of the generator. So even if you have like, n to the 10 different methods, and you're like, well, maybe like on average, one of these methods can do a good job of breaking things. The idea is like, that's
Mhm.
still okay, because like 1 over n to the 10 is like not negligible. So like it's sufficiently large that it, is like counts by definition as like a good break.
Ah, I see. That makes sense. Cool. Yeah.
Okay, cool. I guess I better wrap it up. But yeah, if you have any more questions, you can leave them at Piazza, and otherwise I'll see you tomorrow.